In this lecture, we're going to discuss the notion of countability, which is one possible size, essentially, of a set, especially an infinite set. So we say a set S is countable if either one of the two things. So first of all, we call all finite sets countable. So if S is finite, which I suppose makes sense from the name, as you can certainly count the elements of a finite set. Or there's another case. So the second case is if S is infinite, and but not just any infinite set will do. So we need there to be a bijection with the natural numbers. So there is a bijection with the natural numbers. So let's call it F from the natural numbers to your set. We could have also said S to N. Reason being, if we have a bijection, it's going to have an inverse function that will also be bijective. Okay. Well, in our language that we've developed so far, another way to say this is cardinality of N, cardinality of S are equal. What does this mean? It just means there's a bijection between the two sets. So countable specifically means we have a bijection with the natural numbers, or we're finite. Okay. I should mention this case 2 here is called, it has its own name. And sometimes we really don't care about finite sets. We just want to talk about infinite sets that have this property. And that's called countably infinite. Okay. So we just want to talk about a set with a bijection to N. You call it countably infinite. Countable means those sets as well as the finite sets. Okay. And so there are many examples, actually, of countable sets. Many, many examples. So examples of countable sets, we have already seen quite a few. Let's start with N itself. Right? If we have a function from N, if we can find a function from N to itself, then we've proved that N is countable. We'll just take the function that maps every element to itself. So also the set of even numbers. So set of even numbers. We proved in the previous lecture that that is countable essentially. We proved there's a bijection from N to 2N. So 2, 4, 6, 8. Doesn't matter whether we start at 0 or not. I mean, the bijection might be slightly different, but essentially you just multiply every natural number by 2 and you get one of these. And that is bijective. So the even numbers are countable. Any finite set is countable. You should keep that in mind. The integers are countable. Even though the integers they seem larger than N in some sense, they are countable. We showed a bijection in the previous lecture. We also showed a bijection from N to N cross N. Ordered pairs, all ordered pairs of natural numbers. Those you can actually just put in bijection with a single copy of the natural numbers. And there are many more. Okay. I actually want to take a closer look at these last two. So they're rather interesting. And again, recall, so we already showed that both these have bijections to N in the previous lecture, so you should definitely take a look at that if you haven't. But those bijections were rather complicated. Like I had a complicated formula doing it. There's an easier way to think about this concept of countability. So another way to think about countability, or even to define countability, but yeah, let's say to think about countability is a set is countable if we can list the elements. We can enumerate the elements. So maybe I should say we can find a way to, or we can describe a way a method or a way to list all the elements. List or enumerate. Okay. What do I mean by that? Well, here's one way to show that z is countable. Z is countable because I can list all the integers, starting from somewhere, right? But then going on. And any finite set, we can certainly list the elements. We can put them in a list. For infinite sets, here's what I mean. So z is countable because we can list the integers, all the integers, and I have to be able to describe a way to do it that'll actually get them all. So here's one way to do it, like this. You can go 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, 5, etc. Okay. And that actually proves that z is countable. As long as this convinces you that we're going to hit every integer, it should certainly convince you. So we get all the positives and all the negatives. You may say, well, wait, what does that have to do with this, right? The bijection from the natural numbers to your set. In fact, it has everything to do with that. It's literally the same thing. So by putting them in a list, I am sort of inherently defining a bijection from the natural numbers to my set. The bijection is you take the position in the list. That's the natural number. So send 1 to the first thing, 2 to the second thing. So really, countability, it's just the ability to list out your elements. Okay. Even if it's an infinite set, as long as we can describe a way, describe a process that will eventually cycle through them all. Okay. So it doesn't have to be in finite time, but yeah, you have to describe a way that will eventually hit every integer, well, any particular integer in some finite amount of time. You won't be able to list through all of them, but for example, is this eventually going to hit the number 127? Yes, it will. Right. Hopefully that's you're convinced of that. Okay. How about n cross n? Let's try to prove it's countable just by trying to list out the elements. So what is n cross n? It's ordered pairs of natural numbers. And one way to represent this, we can sort of use a grid. So maybe I'll just put my natural numbers. This page already has some dots on it, so I'll just use those. So you can think of the natural numbers as a 2 by 2 infinite grid. And it goes infinitely down and to the right, for example. So, oh wait, where are the natural numbers? So here's what I mean. So you've got 1, 2, 3, 4, 5, 6, etc. You have an x coordinate and a y coordinate, essentially. 1, 2, 3, 4, 5, 6. So, for example, that dot there would be 5, comma 2. So this is the natural way to think about n cross n. It's this grid of points. Okay. So, making a little table like this. Okay, and recall in the previous lecture, I actually gave you quite a nice formula that actually puts this in bijection. It's an explicit formula that puts it in bijection with n. But we don't need to do that. It's kind of nice to have that, but here's how I can convince you that this is in bijection with n. I'm just going to list all these points. And I'm just going to show you on the graph how I would do it. So maybe I would go like this, and then I would list these 2, and then I would list these 3, and then these 4. See, I'm choosing these diagonals because I know that will sweep out the whole grid, right? Because you need to come up with a strategy that will eventually hit every point in some finite amount of time. Like any one point, you need to be able to get to that point. Okay, so that does it. And what would this look like? It would look like if you wrote out the list, it would be like 1, comma 1, and then I go down to here. So I go 2, comma 1, then 1, comma 2, and then 3 comma 1, and 2 comma 2, and 1 comma 3, then 4 comma 1, etc. So it's kind of like, I mean, one way to think of it is the coordinates sum to 2 here, and here the coordinates sum to 3, so I'm listing out all the ways to do that, and I'm listing out all the ways to make the coordinates sum to 4, etc. So I'll hit everything, including, you know, any point down here. I'm eventually going to choose a diagonal, and I'll go through that. Okay. Maybe before we go on, I want to make something clear. So here's one way that you cannot prove it. So, you cannot do the following method of listing. So, here, let me just make a grid of dots really quick, just to show you what I mean. Okay, I don't need as many to make the points here, but so we've got our same table going on here. And here's what you cannot do. You cannot say, I'm going to list them all in the following way. I'm going to first go down column 1. Then I'll go down column 2. Then I'll go down column 3. Okay. Say, well, wait, why can't I do that? That's going to hit all of them. And sure, I mean, these lines are going to run through everything. However, there is no, you know, go down column 1, then go down column 2, because column 1 is an infinite length. So I'll never get to the end of column 1. Right? I will never get to the end of this column. So this is not a method for listing out all the elements. This does not convince me that we're ever going to get to this element, for example. Right? Whereas this method does. This really is going to sweep through all the elements. Make these a little bit nicer. This is going to hit every element, right? So that's why we do this this diagonal strategy of listing all the elements. Okay, so hopefully that makes sense here. This one doesn't work because I will never finish going down the first column. Same with the integers. I can't just say list all the positive ones, then list all the negative ones. There is no and then, right? It's like you can't ever finish listing the positive ones. So that even though z is countable, that argument would not convince me that it's countable. This one would. This alternating idea. Okay. Great. Okay. So n cross n is countable. Z cross z is also countable. Why is that? It's essentially because you can do the same thing, right? It's because z cross z, so it's countable. Why is it countable? Well, because z is in bijection with n already. So instead of labeling these columns and rows with the natural numbers, I could label them with this bijection. So I can imagine just having all the integers being my labels instead. And that's because, again, z is countable. So I can list them out like this. So same here. Okay. So the next interesting question, and this one has maybe a surprising answer. So what's a bigger set than z? Q, the rational numbers. Is Q countable? Okay. And I've got to be honest, when I first considered this problem, I didn't know the answer ahead of time. And I thought, like, oh, probably not, because I mean, if we have our integers going along a number line, those are just discrete points, right? They're just a series of points. And Q is every rational number, so all fractions of integers. So if you look between two integers, like 0 and 1, you will actually find infinitely many rational numbers just between two integers. Right? You can just keep zooming in and you'll keep finding more and more rational numbers. Infinitely many just in that interval. So it seems like there are quite a lot more elements of Q than there are Z in that sense, at least. But actually, it turns out that Q is countable. So you can actually put all the rational numbers, that set of all the rational numbers, just in bijection with a single copy of the natural numbers. You can describe a way to list them all. Which, again, I found very surprising initially. But the idea is you just view a fraction as So let's say A over B, and maybe we can assume a few things. So like let's say A and B are co-prime integers. Co-prime meaning it's in lowest terms. So there's no common factors. And what else? Like just avoid ambiguity. Let's say A is the positive one. If it's a negative fraction, let's put a negative sign with B. So A is greater or equal to 0. So yeah, we view a fraction like this as an ordered pair of integers. Ordered pair of integers. Okay. What's the ordered pair? It's just numerator, comma, denominator. Right? So we can actually view a fraction as an ordered pair of integers. So it's just a point on this grid somewhere. And we proved that entire grid is countable, right? So we actually have a subset of a countable set here. We can view Q as a subset. So we can view all the rational numbers as a subset of Z cross Z, set of all ordered pairs of integers. Okay, and this is countable. And so intuitively, a subset of a countable set should be countable, right? If you have a smaller set, that should certainly be countable. What's the reason? What's the reason for that? So why is there going to be a bijection of the smaller set to n? Let's state that actually as a theorem. So maybe we won't prove the whole thing, but I'll give you the idea of the proof. So any subset of a countable set is certainly going to be countable. Hopefully that's your intuition at least. Including finite subsets, right? So it even works for that because countable includes finite. Is countable. And the sketch of the proof, maybe I'll call it. Well, let's say we have some set S. So S is going to be, let's call it A1, A2. By the way, how do I know I can list the elements like this? Well, it's because it's countable. Right? So we can actually put the elements in a list. So we're using the fact that S is countable. And so we've sort of assigned each. Like, again, what are we doing? We're assigning everything a natural number. So it's like 1, 2, 3, 4, 5, 6. So here's my bijection with n. So we use the fact that S is countable. We list those all out. So let's do it this way this time. Okay. Okay, any subset of that is also going to be countable. Why is that? Well, let's take a subset. So let's say we, I don't know. Let's take this one and maybe these two and etc. Like you can have an infinite subset, and then you just consider that part of the bijection. So that subset is going to be in bijection with a subset of the natural numbers. Why is that countable? Well, it's because all you do is you say, okay, what's the smallest natural number? Send that to 1. So I've got my third copy of the natural numbers down here, my second copy, I guess. I'll send the first element to 1. I'll send whatever the next element is to 2, then to 3, then to 4, etc. Okay. And if you compose these two functions, that's going to be a bijection of my subset with the natural numbers. So again, here's my other copy of the natural numbers. And that sort of finishes up the proof that Q is countable. So why is Q countable? It's because it can be viewed as a subset of Z cross C, and Z cross C is countable. Okay, so before ending this video, I'd like to actually leave you with one question. The question is, let's motivate this a little bit. So we found Z is countable. We found surprisingly that Q is countable, but then when you go through the argument, maybe it's not so surprising after all. And Q seemed much, much larger than Z, and it was still countable. You could still put it in bijection with just one copy of the natural numbers. So the next question would be, is every set countable? Is every set countable? And what's the answer to that? Okay, I'll tell you the answer to it. It's actually no, but that'll wait till the next video. So I'll give you an example of an uncountable set that you're all familiar with, actually. All right, thanks for watching.